In this video, we're going to talk about tangent planes and linear approximations. So, if you remember back to algebra class where you did equations of lines, or things that look like point slope form of lines, if you will, you know that you can write a line through a point x naught, y naught as y, or say even y1 or x1, y1. You can write it as y minus y1 equals m times x minus x1. You can rearrange that to look like basically this part of that expression without the z's. Okay, so for a plane, that's basically kind of the three-dimensional analog, if you will, of a line. We can write it as a times x naught minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. You can tell that the x naught, y naught, z naught satisfy that equation, certainly. That would be on that surface. And in general, you get a plane when you have that type of an equation. Notice that we can rearrange this so that we have z minus z naught out in front, and then we would have different numbers when we divide through by the c. So we have little a times x naught minus y, x minus x naught, and then b times y minus y naught. What we're interested in is finding what we refer to as a tangent plane to a surface. So here's a surface, here's a point. You see, kind of see the dot back in there. We want the plane that comes along and touches the surface at that point and then keeps going on. But again, it's a three-dimensional analog of a tangent line. So here's that point, here's your surface. It's just going in, touching at that point, and continuing on. Okay? That's what we mean by tangent plane. If I want to figure out this tangent plane, then I need to figure out what those values of A and B are. Okay? Alright, so let's see what we have to do that. So first, let's say we hold the y equal to y naught constant. Okay? So if y, we're looking at, in this case, say along this green line here, holding y constant, what goes on? Well, if we hold y equal to y naught, then this term goes away. Okay? So really we're just looking for an equation of a tangent line, just like what we did before in Calc 1. Remember, for our equation of the tangent line in Calc 1, we had to take the derivative and plug in the point. Well, in this case, we want the partial derivative of x, of f with respect to x, and then we'll plug in the point. That'll give us the slope of the tangent line in the x direction. Do the exact same thing for the y direction. Hold x equal to x naught constant, and then take the derivative in the y direction to find that tangent line. And so then that a and that b have to be those values that we just found that are the slope of the tangent lines in the x direction and the slope of the tangent line in the y direction. So here from the picture, here we held, this one here is representing holding y equal to y naught constant and let the x's change, because the red graph here, the red line here is the x-axis. This one represents holding x equal to x naught constant, and then this is the tangent line in the y direction, holding y or x equal to x naught constant. Alright, so let's see if we can do this. Find the equation of the tangent plane of that function at the point 1, 0, 1. Take our partial with respect to x first. This has a y in it, it's just a constant, so we get 3x squared e to the y. This part here, cosine of y is treated as a constant, so plug it, take the derivative of the natural log of x, we get cosine of y over x. If we plug in the point 1, 0, plug in the x equals 1 and y equals 0, we get 2 for the slope in the x direction. Do the exact same thing for y. Derivative of e to the y is e to the y. Derivative of minus cosine y is plus sine y. Plug in 1, 0 again, and we get 1. So now, the equation of the tangent plane, according to the formula we had, z minus 1, because that's the z coordinate, equals 2 times x minus 1, that's the x coordinate, plus 1 times y minus 1, or excuse me, y minus 0, because that's the y coordinate. So that's why it's just plus y. And then if you really want to, you can rearrange the equation to solve for z. Alright, so looking back at the formula for the equation of the tangent plane, notice that z minus z naught is a change of z. So what that is, much like what we do for tangent lines back in Calc 1, the z minus z naught is approximating the change in the function. right? It's a difference between where the function started, z naught, and where it ended up, the new z coordinate. The x minus x naught and y minus y naught are the changes in the x values. Those are your dx and your dy. So we refer to this as the total differential of a function. So change in z is equal to partial times change in partial with respect to x times change in x plus partial with respect to y times change in y. And we can extend this to functions of more than two variables. Just keep adding on partials and changes in those variables. So let's look at an example of that. So let's use the total differential to approximate this nasty looking cube root. I mean, honestly, that's what calculators are for nowadays, but it gives you the illustration of what you want to do if you're trying to approximate a quantity using differentials. All right, so for that particular case, we want to identify a function and an easily evaluated point of that function. Okay, so the function's pretty clear. I've got a number cubed plus another number squared. So the function must be cube root of x cubed plus y plus z squared. And I know it's a function of three variables because there's three different numbers, right? It's not the same number in different places. It's really three different numbers, so I have to have three different variables. The next thing I notice is each of those numbers are close to 2, 3, and 4 respectively. So I plug in 2 for x, 3 for y, 4 for z, and I get 3. This is what I meant by a point at which the function is easily evaluated. It's also pretty obvious when they give you things in terms of decimals that are close to whole numbers that you probably want to use the whole numbers to plug into the function. Okay, so we're going to estimate the change of f when the point goes from 2, 3, 4, where we have a known value, to the point 1.97, 3.05, 4.02, an unknown value for the function. So in this case, going back to the original function, we'll take our partials with respect to x, with respect to y, and with respect to z. They're all similar. This is inside raised to the 1/3. So you'll get 1/3 expression to the negative 2/3. So that's why we've got this down in the denominator for each of them. And then you have to do the derivative of the inside with respect to each of the individual variables. For x, the derivative will be 3x squared. That'll be on top. For y, the derivative will just be 1. For z, the derivative will be 2z. Plug in your point, 2, 3, 4, and get the values for your slopes. 4/3, 1/9, 8/9. Now we need to approximate get our actual values for change in x, change in y, change in z. Well, we went from the point 2, 3, 4 to the point 1.97, 3.05, 4.02. So so x went down 3/100, y went up 5/100, z went up 2/100. All right, so let's do the total differential now. The change in f, or the differential of f, is partial times differential of x, partial of x with differential of x, partial of y, differential of y, partial z, differential of z. That's our total differential in three variables in this case. Plug in our values. Partial times change for each of the three variables. Simplify, we get negative 1/60. Now remember, that's not the function value, that's the change, right? That's df. So to approximate the function value, we go from where we started plus the change. Well, where we started was 3. The change was negative 1/60, so we get 179/60 as our approximated value for the function. All right. So some problems will ask you for the linearization of a function. Linearization is just literally find the tangent plane, solve for z. Call it L. Okay? So here's a function f of xy equals x squared y minus log of xy minus 7. We're going to evaluate this, find the linearization at the point 2, 4. Do the exact same thing we talked about for finding tangent planes. The function value is 16, so that'll be the z naught from before. Partial with respect to x, 2x times y minus 1 over the inside times the derivative of the inside. Derivative of xy with respect to x is a y. Plug in the 0.24, we get 12. Do the exact same thing for y. Derivative of x squared y with respect to y is just x squared. Derivative of the natural log is 1 over the inside times the derivative of the inside. In this case, we're differentiating the y, so we're left with x. Plug in the 0.2 comma 4, you get 2. Then your equation of your tangent plane would be z minus z naught equals 12 times x minus 2 plus 2 times y minus 4. All the linearization says is you would move that minus 16 to the right-hand side and make it a plus 16. And that should be a plus sign here instead of a minus. So that should be a plus 16 right there. It's just a typo.